Let's talk about some key properties of the tensor product. So here's the first property. So some properties. So the first one concerns what happens when you take tensor products of direct sums of modules. Okay, so let me tell you what the statement is. So suppose I take a direct sum of two modules M1 direct sum M2 and then try to tensor the resultant with n, then the claim is that this is the same, it's isomorphic to M1 tensor n, this is one module, direct sum M2 tensor n. Okay, so of course now when I say this, we need to be a bit careful with what is it a module over and so on. So let's say this is a tensor product over the ring R. Okay, so what sort of objects should M1 and M2 be? So I should assume M1, M2 are right R modules. Okay, and N is a left R module. So this is the very least I require. Only then can I actually construct this tensor product even. And when I say isomorphism, what do I mean by isomorphism? So observe both left and right hand sides are, well, they are Z modules in general, right, abelian groups, and this is an isomorphism of Z modules. In other words, it's a group homomorphism between these abelian groups. It's an isomorphism of Z modules. So this is the first property, and of course this is sort of only the bare minimum, but recall we sort of said typically if you had not just right or left modules but rather some bimodule structures. So more generally you could also have this statement phrased as follows. So suppose let's do brown. So if M1 M2 are not just right R modules, but let's say there is some ring S for which it's a left module as well as. So it's an SR bimodule. Okay, and N is RT bimodule. So here R, S and T are rings. Then still the same, the both sides, the left hand, right hand sides here, they also become bimodules. In fact, they become ST bimodules. Then the isomorphism that we talk about, then left hand side, so let me write it like this, left hand side is isomorphic to the right hand side as not just Z modules but as ST bimodules. Okay, this is further, so this is an additional thing. If I also had this additional structure, then this isomorphism also respects that additional structure. Okay. So let me just indicate briefly how the proof goes and leave it as an exercise for you to actually carry out the details. So what does one have to do? One has to construct maps from the left hand side to the right hand side and in the opposite direction such that their composition is the identity. Okay. So let's try and construct maps. So how does one do it? So let's see. So let's try to construct a map. So I somehow want a map from M1 direct sum M2 tensor n to some other module, right, to the right hand side. Now whenever you want to construct a map from a tensor product to something, what that really means is you should try and construct a R balanced Z bilinear map from M1 direct sum M2 cross n to the right hand side. Okay, so since I know that I am trying to get a map from the tensor product, I will sort of back up one more step and instead try to construct a map. So instead let's do the following. Let's consider M1 direct sum M2 cross n to the right hand side. Let's try to construct a map F. The right hand side, recall, is M1 tensor n direct sum M2 tensor n. And more or less the definition itself is, so this is M1 comma M2, that's an element here, and from n if I pick an element, so it's like I'm taking a triple of elements M1, M2 and n, and from that I need to somehow construct an element in the right hand side. So there is one obvious choice. I just do M1 tensor n. So by the way, all these tensors are over R, comma M2 tensor n. So recall the direct sum is as a set, it was just the cross product, right? So let me define the map in this way, and then we just need to check the following facts, which I leave for you to check as an exercise. F is Z bilinear, and R balanced. Okay, so check these two properties. Now once you do that, what it implies is by the universal property. So once you do this, then this implies by the universal property of the tensor products, by the universal property of, there exists a unique map F tilde from M1 direct sum M2 tensor n to the right hand side. Okay, this is what sort of map is this? It's a Z linear map, and which does the following, which sends M1 comma M2 tensor n to whatever the map F sends it to, which is M1 tensor n. Okay, so what you have managed to do is to use the universal property to construct a map in one direction, and then, you know, by a similar token, similarly construct a map in the reverse direction. Okay, and I mean, you sort of know what it needs to do. We want the composition to be the identity. So just show that there will always exist a map in the reverse direction by sort of again using the universal property of the of direct sums and tensor products. Okay, so let me just say using the universal property of the direct sum and the tensor product. Okay, so recall by the universal property of the direct sum. So recall the direct sum you learnt in categories and functors. This is just the co-product in the category of modules. Okay, modules over, so in this case they are both right R modules if you wish. So this is or Z modules, right? So it depends on what we are talking about, but in general, depending on what ring is the underlying ring, it's a co-product in the category of modules over any given ring. Okay, so co-product of course has this universal property that if you have maps from the two modules some other module, then that map factors uniquely through the co-product. Okay, so use that and use the universal property of the tensor product. Okay, so I'm just going to leave this as an exercise. It's fairly routine. We sort of know what the map needs to be. You know, it's just that you need to show it's well defined is really where the key. So in all these things with tensor products, it's well definedness that one needs to work a little bit for. Okay, good. So so this is the statement here that if I take the direct sum tensor n, it's M1 tensor n direct sum M2 tensor n. Okay, as Z modules or more generally as ST bimodules. Okay, let me state property number 2. Again, I am not going to prove this, but leave this as an exercise instead. So suppose I have a tensor product of 3 modules. So suppose I do M1 tensor M2, okay, over R, and then I take the tensor product of the answer over a third module. Okay, so now here in general this is over some other ring in general S. Okay, so I want to construct, I want to consider such tensor products, threefold tensor products, where, and now let's just do everything in the bimodule situation most generally. So what do I want M1 to be, where M1 is so it's definitely a right R module, and on the left I need to have some module. So maybe I'll call it T1, maybe I'll just call it T. So it's a TR by module. So I'm just putting in the minimal requirement. It's a TR by module. What is M2? M2 is RS by module. Okay, so suppose I do this, then observe this implies in particular that M1 tensor M2, therefore M1 tensor M2 is a ST by module, sorry, TS by module. Okay, and so since it's a TS by module, the S is on the right, I can further tensor product it over S with some other module M3, provided M3 is a SU by module, let's say. Okay, so I suppose I'm given M1, M2, M3 like this, then this sort of iterated tensor product makes sense. And my claim is that this is isomorphic to, so sort of like an associativity property. I first tensor product M2 and M3 together over S. Okay, now the resulting answer is what by module is this now? M2 was an R. This is an RU by module now, the tensor product. And now I tensor it over R with M1. So the resulting answer will become a TU by module. So both sides observe are TU by modules. Okay. So the claim is that this is an isomorphism of TU by modules. Okay, again I'm not going to prove this. Proof exercise, again it's the map itself is more or less, you know, you will have to construct the map similarly by trying to construct you know, Z bilinear, R balanced maps and so on. But the idea itself is that you should map this element here to the corresponding element M1 tensor, M2 tensor, M3. So the claim is that this is what the final, this is what the map finally does, the isomorphisms. Okay, but to, you know, again you can't use this as the definition because of well-definedness will become a problem. So you go back to the definition, use R balanced maps and bilinearity and so on, and the universal property of tensor products to actually construct these maps in a well-defined fashion. Okay, so this isomorphism that you are looking for does this. Okay, so proof again, exercise. So you've seen this many times. Now property number 3 again, which is but this is special for commutative rings. So let me just say R is commutative. So this is sort of a commutativity property if you wish. So you can think of the first thing as being some kind of distributivity property for the tensor product. Tensor products distribute over direct sums. The second is an associativity property of tensor products. And the third is a commutativity property of tensor products, but that only holds if the ring, the underlying ring R is commutative. Okay, so let R be commutative ring and Mn be R modules. Okay, then now why do I want this? I want to be able to construct M tensor n as well as N tensor m, right? So observe, in order to talk about M tensor n in general, I only need M to be a right R module, okay, and N to be a left R module. But then on the right hand side, I have them in the opposite order. So then for the right hand side to make sense, I will need M to be a left R module as well, and N should be a right R module. Okay. So at the very least, for both left and right hand sides to make sense, I will need both M and N to be RR by modules at least. Okay, but that's not enough in general. Just having, you know, a sort of left and right R action is not enough. You know, compatible actions. I need those two actions to be the same action. Okay, only then will this isomorphism work here. So then the claim is that these two things are isomorphic. In fact, saying something more, the map, the isomorphism sends the element M tensor n to the element N tensor m, okay, for all M in M and N in M. So recall such elements generate the two tensor products. So claim is that these elements M tensor N's are just being mapped to the corresponding elements N tensor N. Okay, good. So again, this is a special property for commutative rings, and again quickly let's just prove this. In this case, recall, since R is commutative, the tensor product, I talked about this earlier, can be thought of as having another universal property, which is that if you take R bilinear maps. So now in order to prove this, let's do the following. Let's consider from M cross N to N tensor M. I will define the following map: M comma N going to N tensor N. Okay, consider this map, let's call it F. Now observe the key property of F is that F is R bilinear, then F is actually R bilinear. So recall, this was an additional property. This is not just R balanced, it's a little bit more for commutative rings. So why is it R bilinear? Well, because of the way the actions are. So again, proof exercise, check that in fact this is R bilinear, and here is where you will use the commutativity of R. Now because F is R bilinear, which implies by the universal property, and this is the extra universal property which holds for the commutative case. There exists a unique F tilde. What sort of map is this? R linear map from M tensor N to such that it maps M tensor N to and that's all we need, because observe F tilde itself is its own inverse. If you do it twice, it's clearly the identity map. Okay, so I mean, maybe I shouldn't call the other map F tilde. So maybe there is a map which does a similar thing in the opposite direction. So maybe we should say switch the roles of N and N similarly. That's really your F tilde inverse. So there exists G tilde from N tensor M to this is again an R linear map. And then observe that F tilde and G tilde are clearly inverses of each other. So this is the identity on N tensor M. Okay, so what this says is that there is sort of a commutativity property as well. Okay, so these are the three important properties in some sense for the tensor product functor that we have constructed.